Welcome. Today we are talking about set operations, properties, and identities. This video is mainly to facilitate future videos on set theory proofs. So these are the fundamentals, the basics of set theory. We're going to talk about the operations and properties and then list some identities. We won't be proving anything today. Perhaps in the future, if we need to, we'll do some proofs on these identities, but in the description, I will put a handy little cheat sheet that will summarize some of the things that we talked about today that you can copy and paste if you need to. So before we start, let's let capital A, capital B, capital C be sets. In other words, that just the convention is that we use capital letters to denote sets. I'm trying to make my C a little fancy so that it denotes a capital. And let's let U be the universe. What I mean by the universe is that every set we can think of will exist in U. You'll see throughout this video, I'll draw a box. This box is U. And so all of these sets, A, B, and C, will exist inside of the universe U. There's some paradoxes involved in set theory. We won't talk about any of those paradoxes today. We just want to establish some basics. And the universe is just that. It's just a universe in which all these things exist. All right, so let's start with what it means to be a member of a set. So membership. So if A is a set, we say that X is in A. This means that X is a member of A. This means element of, and sometimes we will say in. So when I read that, I will say X is in A, or X is a member of A, or X is an element of A. All of that will mean the same thing. If something is not an element, X here is small. It's not a capital X. So if I say this, I mean that X is not a member of B. So cross through the element symbol, it's that E means not in. So we can also think of this as not in B. This comes in handy. It might not seem relevant, but it will be used throughout. So that's what it means to be in a set. Let's take a note here that sets can also be inside other sets. So if I say X is an element of A, capital X, I'm meaning that the set is a member of the set A, which will be confusing until you get the hang of the sets here, but we'll talk about that later. So let's talk about what it means to be a subset. This will be notationally look like this. A is a subset of B. This notation means subset or equal. That's what the little bar below the C symbol looking thing means, possibly equal. So what is, by definition, what does it mean to be a subset? It means that all elements all the elements of A are also elements of B. Another way to write this is that if X is in A, and A is a subset of B, then X is in B. We know that by the fact that A is a subset of B. This will be automatic. A visual of this, if I were to write this, would, if this circle here is all of B, then this circle inside of B is the set A. And you can see all the elements of A are in B. That's what it means to be a subset. This leads us to a proper subset. Now, when I write subsets, I usually write the subset equal to symbol, the one above, just out of habit. But when we know that a set, like in my diagram, that A is contained in B, we can see that there's possibly some elements in B that aren't in A. And this is the condition where we say A is a subset of B. That means that there are some elements in B that aren't in A. So while all elements X in A, X will be in B, there might be some elements in A some elements in B that we know are not in A. Now, the distinction here is maybe not so apparent. I generally use proper subsets when I know that A and B, in this case, would be different sets. If I don't know, I always use the possibility that they're the same. So let's look at an example. Let's say that A is the set that has the elements 1 and 2. My little squiggly, the notation, this means that everything in here is a member of the set. So everything in here is of the set, in the set. My squiggly notation is terrible. It's not something that I've worked on, but that's just what it is. So it's called set builder, right? If you've taken college algebra, that should be familiar. So let's let A be the set that has 1, 2. Let's B be the set that has 1, 2, and 3. Then we can see that A is a proper subset of B. A has 1, 2, which is also in B, and B has 3, which is not an element at A. So there's no possibility that A and B are equal. So this is a proper subset. So this leads us to equality. So if we say that A and B are the same sets, let's write it that way, language-wise. If A equals B, then A is a subset of B and B is a subset of A. So this is important when we are proving set equalities. If I have two sets that I want to prove that are the same, what I'll do is I will show that one is a subset of the other and then do the opposite direction. So in other words, if I want to prove that, say, X and Z are the same sets, first I prove that X is a subset of Z. Then I prove that Z is a subset of X. And once I've done that, I've proven equality. So equal sets means that they're both subsets of each other. All right, so we have U as a universe. So let's talk a little bit just so we have this, the set U is everything. It's the universe that we're interested in. Now, if I have sets A and B, it's natural that A is a subset of U and B is a subset of U. Right? They're in the universe, so they're subsets. Everything in A is in U, everything in B is in U. In fact, any set that we find, if we define our universe as being complete, then All of our sets are in that universe. I mentioned that because I want to write some diagrams for some of these set operations, and I want to establish that the universe and that these sets are subsets of that universe. So here's our first true operation, which we call union. And the definition is that if A is unioned with B, we're going to define that as being all the elements X in the universe such that X is in A or X is in B. Now this or symbol, I'm just going to write out ors and ands throughout this video. Logic, symbolic logic has this is being or, which is the same as the union symbol, but this is a sort of a V. I won't be using the V. I don't want to confuse it. So I'm just going to write or. So for an element to be in the union of two sets, it has to be in one or the other sets. A picture of that is if I have my universe box here, and I have A and B, these are sets A and B, the union will be everything in both sets combined. That's where the or statement comes. X is in A or X is in B. That's our collection. That's our union. So it needs to be in both. Let's do an element example. Let's let A equal 1, 2, 3. I'm going to do all finite sets for these examples. If you want to see more complicated infinite sets, let me know in the comments. I can do another video where we talk about more complicated looking examples. But for now, I'm just going to use really simple examples just to illustrate the point. So A union B here, I'm going to collect everything in A and everything in B into one set, but I'm not going to reproduce elements. So we can see 2 is in both sets, but I'm not going to write 2 twice. We don't ever write the element twice. So we got 1, 2, 3, 4, 6. So that's the union of A and B in our example. That's the definition. Again, note that union, it'll be equivalent to an or statement. And this is handy if you're going to study symbolic logic in any sense that the logical or is the same as a union. And if you want to sort of further the analogy, this is also addition. Arithmetic or is addition. Okay, so let's talk about intersection now. So this is another set operation. So when we say that A intersects B, and that symbol is the sort of upside down U, we define this as being all elements X in the universe such that X is in A and X is in B. So you see the condition is that it's in both. So intersection and produces, again, this is our universe box. Here's A, here's B. I didn't like that. So here's A, here's B. The intersection is what they have in common, right? It's X is in A and X is in B. Now, it's possible that the intersection is empty, that these two sets don't have anything in common. My diagram is when they do have something in common. So again, let's do an example. Let's let A be 1, 2, and 3. And let's B be 2, 4, 6. And then the intersection of A and B will be only the elements that they have in common. So what do both sets have in common? Meaning, what are both sets overlap? we can see that A has 1, 2, 3, B has 2, 4, 6. So the only thing they have in common is 2. So the intersection of A and B is just 2. And again, we should think of and as being the intersection. And we could think of it symbolically, logically, as the sort of caret symbol. And we can also think of this as being multiplication. We're not going to talk about multiplication and the symbolic logic here, but just as a sort of handy little reminder that that is true. So that's the first two operations, union, intersection, which again is sort of parallel to the addition and multiplication. Now let's look at what's called the difference of sets. There's a couple notations here. So I like the sort of subtraction notation, where it's A minus B. I keep hitting this button. But you will also see this notation. Both mean A without B or A not B. However you want to say it, it's the same. And the definition is simply that A not B or A without B is all the elements, again, in the universe, such that this vertical line means such that. If you're not familiar. And what we sort of block out the set builder by saying, oh, we're going to collect all the elements such that, and then have our rule or our definition. So X is in U, X is in the universe means that we want to collect all the elements that are in A and all the elements that are not in B, meaning that this is the definition. If A not B means I collect all the elements in A and throw out anything that it has in common with B. That's the difference of sets A and B. Now the visual, again, here's our universe. Here's A and B. It'll be everything not in, or everything in A that doesn't touch B. So it's that little portion there. So let's do an example. We'll have A equal 1, 2, 3 again. B equals 2, 4, 6. So A not B. One way you can do this really simply is if you want to, you can just write down everything that's in A and then erase everything that you see that's in B. So if I wrote 1, 2, and 3, that's what's in A. Now I have to get rid of 2 because 2 is in B. I can't use that. 4 is not in there. 6 is not in there. So A not B is just the set that has 1 and 3. My squigglies are bad, but my set notation is not great. Hopefully this won't ruin things. The squiggles are always the start of the set and then the end of the set. So that's what A not B is, or the difference of sets. I think from here on out, I might say A not B. Now this will naturally go towards the complement of a set. And we have two notations. We have the A bar, or the A with the C as a sort of power. Now that's not A raised to the C power. That's the complement of A. And it's defined this way. So here again, was the universe is important. Not things that are not in A will be all the elements in the universe such that the element is not in A. So what does that mean? Let's look at a picture again. So here's our universe, and here's the set A. By this definition, the A complement is all of the things outside of A. So all of this is not A. You can always think of this as the opposite of A. All the things that are in A will not be in not A. So let's use an example. Now I have to define the universe. This universe will be small, so it won't be all encompassing, but just for this example, let's have the universe be the set that has all the integers 1 through 10. And let's let A be the set that has 1, 2, 3, and 4. So the complement of A are all of the elements that are in the universe, and then we throw A out. So we don't use 1, 2, 3, 4. So then the complement is 5, 6, 7, 8, 9, and 10. So you can see it's sort of the opposite, right? Not A is this sort of the opposite of A. So that's the complement. We always have to define the complement in terms of the universe we're in. So if you have a parent set, the large set, if I say A is a subset of X, a complement will be all the elements in X that are not in A, or the stuff we throw out of A. Now let's look at something that's not widely used, but definitely turns up a lot in a discrete mathematics class and an intro to analysis class. And these properties and definitions and operations you will find a lot in, say, introduction chapters or sections to a topology textbook or to a real analysis textbook. They might pop up sometimes in abstract algebra, but it's ubiquitous throughout mathematics. So set theory is always present. I'm never surprised when I look at a textbook and chapter 1 is always the beginning of set theory. So this this video would be put in playlists that would be any number of those areas of math. So this notation, I like this notation. It reminds me of the zodiac symbol. So we're defining the symmetric difference, this little symbol with a circle with a plus in it, is A not B union with B not A. So you might ask, that's a very weird way to define a set, right? All the stuff that's in A but not in B, and all the stuff that's in B and not in A. The way I like to think of the symmetric difference, and I think this is a more appropriate term for it, is the anti-intersection. That's sort of my own term. When I help students or students ask me questions about the symmetric difference, I always tell them to think of it as the anti-intersection, and that'll become apparent when we write this out. So here's the universe, and here's A and B. So by this definition, we have all the things that are in A, and then we throw out the stuff that's in B. So that means we have this portion. The second portion is all the stuff that's in B, throwing out the stuff that's in A. So that's this. So you can see that the symmetric difference is really the union of A and B, and we throw out the intersection. So in a sense, it's the anti-intersection. Again, my terminology. I don't know how consistent that terminology is, but it helps me remember. It might help you remember. So that's a symmetric difference. Let's look at an example, an element example. The picture is helpful. I like to collect the elements sometimes just so we get a sense of what it would look like element-wise if we had to do it that way. So one way to do this is to do A not B, and then do B not A, and the collect of both of them. Doing that, we would yield 1, 3, 5, 6, 8, 10. because we can see 1 is in A but not in B, but 2 is in A and B, so we have to throw out 2. 3 is in A but not B, that's good. Now 4 is in both, so we have to throw that out. 5 is not in both. 6 is not in both, and 8 and 10. So really, if you have two sets and they're finite and you can list them, you really just need to get rid of the things that are in both. So again, anti-intersection. Not entirely common. Some classes, some professors like the anti-intersection, and you'll do some proofs with it. But it's not too common. This, on the other hand, is incredibly common. It comes up everywhere. Cartesian product. You can think of this as a cross product. Now, I'm going to do a two-set cross product. I'm not going to go through the cross products of A cross B, C, D. We'll just do A and B at this point. If you study topology, there is a topology built on the product. But for here, we're just going to do this. So Cartesian refers to the Cartesian coordinate, which is a graph in XY terms. And we know when we have a point here, we have an X coordinate and a Y coordinate. Now, we sort of formalize this by saying that if I have two sets A and B, the Cartesian product of A and B will be equal to the coordinate pair XY such that the first component is a member of the set A and the second component, Y, is a member of the set B. So if I have a Cartesian product, I have a collection of XY coordinates where the first component is a member of A and the second component is a member of B. Now, let's look at an example element-wise. There isn't really a graph other than what I've just shown here. One thing maybe to note is if I have, let's say, I could have a function, let's say I have a linear function, I can define the Cartesian product by this function and say that A cross B will be only the coordinates that are on this line. But let's look at it element-wise. So again, an example, let's let A equal 1 and 2. I don't want it to be too big, and for that, you'll see why. And B to be 4, 5. So A cross B is going to be a collection, again, of ordered pairs XY. We call them ordered because the first coordinate is from A, the second coordinate's from B. And so we do that. We do every combination we can find of the first coordinate 1. So we do 1 and 4. Then we do this 1 and 5. And that's it for 1. And then we do the first coordinate, we'll use 2. So 2 and 4, and then 2 and 5. So that is the Cartesian product of A cross B, given that A is 1, 2, and B is 4, 5. Now, this graph isn't going to be that accurate, but if I were to graph this, I would have, say, 1, 2, 3, 4, 5. 2, 3, 4, 5. So 1, 4, 1, 5. And then 2, 4, and 2, 5 would be this. So this here is A cross B, given my example. It's those points there. Again, cross product comes up everywhere. So if you are studying mathematics and you're just starting out and you're taking discrete math, or you're in college algebra and you watch this video just out of curiosity, that the Cartesian product stuff will be ubiquitous throughout math, as will this. And this, there's not a ton to say about it. The empty set, which we symbolically denote this way, 0 with a line through it, or O with a line through it. This is the set with no elements. There is nothing in the empty set, hence it's named the empty set. No elements in here. Now, an interesting fact about the empty set is the empty set is a subset of every single set. This is vacuously true because remember the definition of a subset means that all elements in A are also in B. That's the definition we have of a subset. Now, it should be obvious that if I have a set A and B, and I have the empty set has no elements, so all its elements are also in A. In fact, all its elements are also in B. No, it's vacuously true because it has no elements. So that's why the empty set is a subset of any set you have. Let's talk about cardinality. When putting this lecture together, it was a little difficult, just like which order should I put stuff in. So hopefully this flows so that you can jump ahead if you need without missing anything important. So the cardinality is a way to say how much or how many elements are in a set. And we denote this by what looks like the absolute value symbol. Yeah, we take two lines between, or put A between two lines. This means the cardinality of A. Now, if A is finite, we just count how many things are in A. So the cardinality will be a number. The cardinality of A is 4. If A is infinite, the cardinality of A would be infinite. Now, this is a whole other conversation I'm not going to go over in this lecture about cardinalities. Cantor proved that there are different cardinalities or different sets of the infinite. But again, I don't want to get into that. That's a whole other video. So the empty set, the cardinality of the empty set is 0. There's nothing in the empty set. Now, the reason that we just sort of jump through the power set or the cardinality is to talk about the power set, because there's some helpful things to remember with the power set. Now, power set, I'll write the notation. The power set of A, and here we have a fancy P. Usually it looks like rho, but it's just a fancy P, denotes the power set of A. Now, what's the power set of A? So the power set is defined as all subsets of a set. So I have the power set of A. What I mean is this. I mean that if I have the power set of A, it's all the sets, capital X, such that X is a subset of A. That's what a power set does. It collects in a set itself of all the subsets of a set. Okay, that's weird, right? Well, an example here, if I have A, 1, 2, and 3, the power set of A will be the collection of subsets of A. Now, remember the definition of a subset. So A is a subset of itself. All the elements in A are also in itself. So then A is a subset of itself. We just showed above that the empty set is a subset of everything. So the empty set is in the power set. Now, every possible subset will be in here too. So The singleton sets will be in here. So the sets that have 1, the set that has 2, the set that has 3, and then every combination of that. So 1 and 2, 1 and 3. That looks too bad. Two and 3. Now we have 1, 2, 3, 4, 5, 6, 7, 8 elements. So I know I'm done. I know this is the power set of A, and I'll explain why in a second. But so let's recap. The power set of A, when A is 1, 2, 3, is the set that has the sets. These are sets. A, the empty set, the set that has 1, the set that has 2, the set that has 3, the set that has 1, 2, the set that has 1, 3, the set that has 2, 3. And we can see the cardinality of the power set of A is equal to 8. So this is a handy little rule here, is that if A is equal to, let's say, n, the cardinality of A has n number of things in it, then the cardinality of the power set will be equal to 2 raised to the n. So in our example here, our A had 3 things in it, and so the power set of A, the cardinality of it, is 2 to the 3, which was 8. So that's how we knew that we were done when we collected all those sets. This is handy. Let's take something perhaps doesn't look too big, but let's say A is a set and the cardinality of A is 10, meaning A has 10 elements in it. It could be 1 through, or 0 through 9, 1 through 10, right? The first 10 letters of the alphabet, whatever it is, it has 10 elements. That means the power set of A, all of the subsets that we can make from that, is equal to 2 raised to the 10th, or 1024. So there are 1024 subsets of A when A has 10 elements. Now that's quite a lot. I'm not going to even begin the list. So that is a handy tool. That theorem, I guess it's a theorem. Let's call it a theorem. I'm not sure it is, but so that's the power set. The power set is all the subsets of A. Again, these are handy in proofs. Maybe it might not seem so relevant right now, but it's sometimes helpful to know how many subsets I have of a set. Now, this is more notation, I guess. But you see this all throughout mathematics. Index sets. We can make sets by some rule, and we can use notation to sort of minimize the complication that might come in with defining a set and having to write hundreds of sets. So I can write something like an index set. Let's use an example. I think that would be the best way to look at these. So I could say let's index a set A sub I will be equal to, say, I and then I plus 1. Now, if I say I is equal to the integers, you can see how it would be handy to define it this way, because now I can just leave it that way and I don't have to write out an infinite list of sets. But as an illustration, let's say that I is just 1, 2, 3, and 4. So this index set, A sub I just look at this index and I start with A sub 1, and then the rule says I replace whatever the subscript is, I, with it, and then I add 1 to it. So then A sub 2, and I'm going to do this throughout the entire index, so 1, 2, 3, and 4. So this is 2 and 3. A sub 3 is 3 and 4. And A sub 4 is 4 and 5. So again, this is a handy notational tool that we can write sets pretty compactly. over some index, and I is the index, and the set 1, 2, 3, and 4 we'll call the index set. So I initially wrote the integer, so that would be the index set. I ranges over the integers, so a sub I would be infinite. There would be infinitely many of them, and we wouldn't want to write them out, but that would indicate to the reader that the index set is all the integers that are 1 and 1 more than it. Or sorry, every integer and then every integer plus 1. But for example, we have 1, 2, 3, and 4. So now we can do set operations on these. Again, notationally, we would write it differently, but you'll see it's exactly the same. I would start with my index. So I'm going to start with I equals 1. Now I'll go to 4 of a sub I. So again, it's nice. It's compact. It says take the union of a sub i's from 1 to 4. The literal translation of this is a sub 1 union a sub 2 union a sub 3 union a sub 4, which if we look at our a sub 1, 2, 3, and 4 above, we can see that this will equal 1, 2, 3, 4, and 5, just as our example. We could also take the intersection of index sets, and this would be a sub 1 intersect with a sub 2, intersect with a sub 3, intersect with a sub 4. And what would this equal? Well, empty. There's nothing they have in common. So index sets are handy. If I had a sub I is equal to I plus 1, I plus 2, and then I had I is a member of the integers. I could take the union of I and the integers of a sub I. And we can see that if I did that, that would equal the integers themselves. So this is a more complicated example, but if you can just get familiar with the index sets using this example, finite example, something small. The larger stuff will make more sense. I did a couple of videos where we're proving something about index sets. And if you want to look at that, I will put a link in the description so you can check those two out. So that's index sets. Now we want to talk about images and pre-images, because these are indeed sets. So before we have to set up what we mean. And so to do this, we need a function from two sets. So I'm going to have f be a function from a to b. And of course, a and b are sets. So a and b are sets. The function takes all the elements in a to some element in b. So f defines a function. Now, a function will take an element, let's say x, into its codomain, where it's f of x. In other words, each x has exactly one output. And we'll call that f of x. And that exists in B where x is in A. That's basically the definition of a function, right? A function takes elements, everything in A will have a mapping to some element in B. Each element will map uniquely to one element in B, but not necessarily will all of the elements in B be mapped from uniquely elements in A. So in other words, if I have A has these two elements and B has this, it's possible that this these two elements map to the same element in B. So this is a function. All right, so what do we call A here? A is a set. So A is the domain. And B is the codomain. So we're mapping A to B. A is domain, B is codomain. Now, notationally, we say that f of A is the image. Sometimes you'll hear this called the range. And f of A is a subset of B. All of the elements of f of A reside in the set B. Now, the preimage we define as being f with the inverse notation, -1 of B. B is looking weird, so let me write that better. Is the preimage. And F, I'm just going to call it the preimage. The preimage of B is a subset of A. All right, before we get into too much of the definitions, let's write out maybe a little diagram of how this is functioning. No pun intended. So this is the set A, this is the set B, and this is f of A. So the function will take all of the things in A and map it to f of A. So that's what f does. F takes everything in A and maps it to that f of A, the image. Now this f inverse B, this preimage, is essentially taking the opposite. It's taking everything in B that has a mapping back in A. So the preimage can be a little bit confusing. Hopefully the image isn't something that you're not unfamiliar with. Let me write out the literal definitions of this. So the set f of A, and it is a set, is all of the elements f of x such that x originates in A. And then the preimage are all the elements x such that f of x is in B. Now, this is just a sort of handy notation of what I set up here, where they reside and how they're defined. Let's look at an example. It might help. Definitions are nice, but let's look at an example and get sort of an idea of like how this works. So we have a function from A to B. And let's say our function is defined as x plus 1. We're just adding 1 to x. So it's a linear. And let's let the domain be 1, 2, 3, 4, and 5. Let's let the codomain be 1, 2, 3, 4, 5, and 6. All right, so what is the image of f of A? This is the image. What is the image? This is all of the elements in A that map to some element in B. So 1, we add 1, we get 2. So 1 goes to 2, and so that's in our image. 2 plus 1 is 3, so that's in our image. 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6. So that's the image of A. And you can see that's a subset of B. So it's the pre-image under the function well, that's going to be 1, 2, 3, 4, 5, and 6. So what you do is you look at all of the elements in B and see if they have a mapping back to A. And then we collect all of the elements in A that this, or elements in B that this is true. Oh, wait, I shouldn't have 6 in it, my fault. So this is essentially A, but you can see f of A is a subset of A. Now the equality is not important, but sort of that's our example. Images and preimages. There's a lot to say about functions and image preimages and composition and other things, but I just wanted to leave that here as a part of my set video, just so I can reference it later. That's no way thorough, but it's just sort of a exposure. Lastly, let's talk about some quick identities. Set identities. I'm not going to prove any of these. If you want to see some of these proved, let me know in the comments, and I'll be more than willing to make a video of that. But these are just some simple sets, identities that will be useful. And again, in the description, you will find a quick list of all of these things that we talked about today. So set operations are commutative. So A union B is the same as B union A. And A intersect B is the same as B intersect, I don't know why I wrote C, A. All right, so they commute, they are associative. I'm going to introduce a new set C here, but essentially A union B union C, I don't need that extra parenthesis. This will be exactly the same as A union B union C. Now, the same is true for intersection. This is equal to A intersect B intersect C. Now, associative might just seem like it's grouping, but you realize that if I take the intersection of A and B on the left first, that set will be different than the intersection of B and C, and then I would intersect the left with C and the right with A. We would end up with the same set, but the steps would look vastly different. So that's associativity. Now, they also distribute. Again, these set identities will distribute. So A intersect B union C will equal A intersect B union A intersect C. So they distribute. Shouldn't be that surprising that this will happen with the operations reversed. So A union with B intersect C will be the same as A union B intersect A union C. Again, it's a good exercise proving these. If you want to see that, please let me know in the comments. So these should feel somewhat algebraic, right? Associativity, distribution, commutativity, identity, somewhat algebraic. So identity means if I take U or A and union it with the empty set, I get A. If I take A and intersect with the empty set, I get the empty set. So this is almost like A plus 0 and A times 0, right? Now, if I take A union with the universe, I get the universe. And if I take A intersect with the universe, I get A. So the identities are similar to multiplication and addition with 1 and 0. Now we have the complement laws. Now remember our notation for a complement. So if I have A union with its complement, this is saying that I take all the elements in A and all the elements that are not in A. If I do that, I get the universe back. If I take A and I intersect with its complement, so I take all the elements in A and I collect what they have in common with not A, it should be obvious that I get the empty set. Lastly, and perhaps and most importantly, if you study symbolic logic, there's something called DeMorgan's laws. There's also DeMorgan's laws of set. We're going to talk about these briefly. And again, if you want to see something more thorough, let me know in the comments. I'll be willing to prove these. This would be a much longer video if that were the case here. So the complement of A union B. So I'm taking all the things that are not in the union of A and B. Well, that's going to be equal to the intersection of the complement of A and B. The same is true if I take the intersection of A and B and I take its complement. This will be the complement of A union the complement of B. So DeMorgan's laws, obviously, they'll work for index sets too. So if you have to work with index sets, DeMorgan's laws apply. In other words, the union, let's say I and the integers of A sub I will be equal to the intersection of the union of integers of A sub I complement. So it works both ways. So in other words, if I have, I'm not defining what these are, but this is just generally true. And this is I in the integers. So it works for index sets. If you write that out, you'll see you'll just get a collection of these. So that's basically how you would prove these two. And that's all I wanted to talk about for this video. I know it was a lot, but again, in the description, you'll see a nice little cheat sheet, a sort of list of the properties and things I talked about in this video. Feel free to copy and paste that if you need to. And that's it. Thank you for watching. Like and subscribe. Let me know if there's anything else you would like to cover, and have a great afternoon.